Hello and welcome, everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please try refreshing your browser. If that does not fix the issue, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we do not address your question, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's webinar will discuss a cost analysis for PFAS remediation at DoD sites. With that, I'd like to introduce our presenter for today. We are pleased to have with us Dr. Jeremy Birnstingl, Vice President of Environmental Technology at Regenesis. Dr. Birnstingl serves as a senior Regenesis technical resource on key remediation projects involving advanced in situ technologies worldwide. He is the author of the Plume Force software used for design and modeling of the Regenesis activated carbon-based technologies. Dr. Birnstingl received a Bachelor's of Science in Environmental Biology from the University of Essex and a PhD in Environmental Chemistry from the University of Lancaster. He is a Fellow of the Royal Society of Chemistry in the United Kingdom and a Chartered Environmentalist. He has 35 years experience in commercial and academic environmental sectors, including 22 years with Regenesis. His creative and scientific insights have been recognized through 3 commercial patents. All right, that concludes our introduction. So now I will hand things over to Dr. Jeremy Birnstingl to get us started.
Thank you, Dane. For this webinar, we're going to look at a formal cost comparison between 2 remediation options for a PFAS plume at the former Wurtsmith US Air Force Base in Oscoda, Michigan. The content is drawn from a formal paper recently published in the Remediation Journal, written by myself and John Wilson. Let's look at the context of this. It'll be no surprise to anyone attending this webinar that per- and polyfluoroalkyl substances, PFAS, represent an emerging environmental challenge. These recent data from the US Department of Defense provide an indication of the actual costs over the last few years and the anticipated costs to come. Faced with billions of dollars in remediation costs, and the cleanup components of the projection you can see is just over $6 billion, the US Congress Appropriations Act last year formally instructed DoD to prioritize technologies that eliminate the PFAS risk to human health and the environment in the most cost-effective and energy-efficient manner. The PFAS problem is not unique to the DoD. A similar challenge is faced by many sectors. What are the available remediation approaches? Well, there are many in development, as we might expect. How many of these are good to go? Members of the US Interstate Technology and Regulatory Council, the ITRC, have put a lot of work into guidance documentation for PFAS. I'd recommend our website as a first stop for most PFAS-related information. The website describes available treatment technologies for PFAS for different media. These are classified based on their state of development, from lab scale to emerging to established. The highest category for establishment is field implemented technologies. These are defined as fulfilling the requirements of being demonstrated to meet cleanup objectives on multiple sites under diverse conditions by multiple practitioners at the intended application scale. Also of being well documented in practice or in peer-reviewed literature, of being widely accepted in the regulatory and scientific communities, and that are commercially available. There are presently just 2 groundwater remediation approaches in this category. They are pump and treat, using various methods for treatment of the extracted water, and in situ remediation with colloidal activated carbon. These are therefore the two approaches evaluated in the Remediation Journal paper published shortly before Christmas and that this webinar draws from. I'll provide the QR code you can see here again at the end of the webinar. I'm most grateful to John Wilson for his important contribution and guidance in producing this. It's been a pleasure and a privilege to work with him. I'd also like to acknowledge Bay West for their assistance, with a particular shout out to Mr. Paul Donovan, PE, at the St. Paul, Minnesota office. Let's address some technology basics as a foundation. First, what is pump and treat? In the context of this analysis, pump and treat is being used to hydraulically contain the PFAS groundwater plume and prevent it from impacting down-gradient receptors. Migrating groundwater is captured by pumping from wells transecting the plume, and the extracted water is then treated. It's passed through activated carbon in the present example, although other treatment approaches exist. The cleaned water is then re-injected some distance down gradient from the extraction points and continues on its way. The spent carbon is sent for treatment or disposal. In terms of remediation, we start with pollutant linkage, the source pathway receptor concept fundamental to risk assessments. The contaminated groundwater is pumped to surface, where it's passed through a treatment system, pump and treat, and the cleaned water is re-injected. The PFAS from the groundwater are collected as a concentrated waste by the treatment system, and this is then sent for disposal. This is the filter room for the Wurtsmith pump and treat system that we'll use as our cost comparison example. What about in situ colloidal activated carbon? The colloidal activated carbon remediation product used for the comparison is sold commercially under the trade name PlumeStop. It is a liquid containing tiny activated carbon particles. These are micron scale, each about the size of a bacterium or a red blood cell, 1,000 times smaller than a particle of granular activated carbon. The proprietary carrier fluid prevents the carbon particles from clumping and supports injection and evenness of distribution, or sweep efficiency. So what does this give us? Think of PlumeStop as an activated carbon ink. It flows, but it sticks. The coating of activated carbon it leaves on the soil particles is micron thin. It therefore does not interfere with groundwater flow. In terms of remediation, let's start with our pollutant linkage again. PlumeStop is injected as a fluid directly into the contaminant plume. It flows between the soil particles and paints them like an ink. The soil particles are now coated with a micron layer of activated carbon. A line of overlapping injections forms a capture barrier. This behaves as an in situ purifying filter. The groundwater continues to flow freely through the barrier. The CAC coating is too thin to measurably disrupt its flow, but the contaminants are stripped from the groundwater by the carbon. The contaminant migration is stopped, plume and stop. The pathway of the pollutant linkage is therefore broken and remediation is secured. In a little more detail, what PlumeStop is essentially doing is slowing the plume velocity by orders of magnitude by increasing the contaminant's retardation factors. A plume advancing at say 100 feet per year would be slowed to maybe an inch per year, for example. The barrier design longevity can be adjusted by changing the quantity of PlumeStop applied. Adding more increases the longevity in direct proportion. How long should a barrier be designed to last? Well, this depends on the project and is answered case by case. Because additional carbon can be added at any time when the source is ongoing, the design may allow for periodic reapplications. These can be at long intervals. In the present costing exercise, for example, the selected minimum longevity increments are 25 years each. This allows the future incremental additions to be better tailored to the plume conditions at that future time. This is what PlumeStop injection looks like. This particular application is in Kenosha, Wisconsin in October 2021. exactly the same time that the Wurtsmith pump and treat system was being extended, and we'll come to that. The injection points we can see sticking up are temporary. 3 or 4 points are being injected in parallel from the mixing trailer in the background, and the rig is moving between them in turn. After injection, all the equipment is cleared from the site, leaving only the carbon in the ground, forming a capture barrier. Nothing visible remains on the surface. Let's get on to the cost comparison and the site background. Wurtsmith Air Force Base is in Oscoda, Michigan, close to the shores of Lake Huron. It's a BRAC site, closed in 1993, and it became a Superfund site the following year. It principally sits on unconsolidated glacial deposits. The target formation is relatively coarse-grained, sandy, and fining upwards. It overlies lake deposits and glacial till. Groundwater is at about 10 feet, and the clay below is at about 40 feet depth. AFF's aqueous film-forming foams were used in fire training, and this paper concerns PFAS from a fire training area close to the site boundary, adjacent to a wetland system that eventually drains into Van Etten Lake and Lake Huron. Here's the fire training area and the plume vector to the wetland, and so we have a source, we have a pathway, and we have a receptor. At the time of the initial remediation system design, the PFAS and PFOA plumes looked like this. They're fairly hot, 10,000 to 100,000 nanograms per litre in the core channel, and the plume is fast. It's in coarse-grained sandy deposits with a steep gradient. The hydraulic conductivity is about 10 to the minus 1 to 10 to the minus 2 centimeters per second, so we're talking about a groundwater seepage velocity of around 1,000 feet per year. This is visible PFAS contamination on Van Etten Lake, way down gradient. And the local residents are none too happy about it. The Air Force did something about it. I'm not sure if this was the very first PFAS cleanup program under Superfund, but it was certainly one of the earliest. A pump and treat system was installed in 2015 as an interim remedial action with the objective of containing PFOS and PFOA concentrations above 20 nanograms and 40 nanograms per litre, respectively. The combined influent concentrations of the pump and treat system on startup were 30 to 300 times higher than these targets, even though they represented a blend of high and low concentrations from individual extraction wells across the plume. Although the remediation requirements are based on PFOS and PFOA only, other PFAS species are of course present. The system extracts 240 gallons per minute, which is about 2.5 million gallons per week. That's equivalent to the average water usage of about 1,000 US families. The cost of the installation, converted to 2024 dollar value, was $3.2 million. Because this is one of the earliest PFAS remediations under CERCLA, the publicly available data and long history make it a good choice of site for this study. In 2022, the system was expanded to accommodate more stringent cleanup targets based on the health advisories published in 2017. The existing extraction array was widened and a second extraction array was installed down gradient. This captured a wider proportion of the plume. It approximately doubled the extraction rate from 240 to 445 gallons per minute. That's now the equivalent water usage rate of about 2,000 US families, enough to supply a village. The cost of the extension was a further $3.4 million at 2024 dollar values. The cost comparison that we're going to look at is built on public domain data, freely available to everyone. Principal sources were the Air Force Civil Engineering Center and State of Michigan databases and report repositories, which hold thousands of records and reports dating back to the 1990s. These include environmental reports, the design and costing reports for the pump and treat system, and the daily monitoring records of the operational system. These were the approaches evaluated in a formal feasibility study in 2014. Can you spot a common technology theme? In situ colloidal activated carbon was not available at that time. In fact, it was launched the same month that the MWH study that we're looking at was published. Hydraulic containment was the selected option. It was the least expensive of the options evaluated, and we'll compare it with colloidal activated carbon shortly. It's worth noting that the estimated time to closure at this time was 30 years, and this is important, not just in relation to closure expectations, but also because the cost estimates are whole project costs and include lifetime operation and maintenance. The expected accuracy range of these projections is stated to be from -20 to -50% on the low side and +30 to 100% on the high side, depending on the technological complexity of the alternative. This means that the pump and treat option 1 was expected to close within 30 years for $6.4 million, with a worst case upper limit of 60 years to closure for less than $13 million in total at 2014 dollar values. How realistic is this? Well, let's explore time to closure. What can we learn from the recorded performance of the installed pump and treat system? This question is relevant to the costing exercise because the cost of a remedy will comprise both the cost of installation, the capital expenditure or CapEx, and the cost of operation, the operational expenditure or OpEx. For the OpEx component, it's necessary to know for how long the operation will continue and therefore for how long the operational costs will continue to accrue. Is the 2014 estimate of 30 years to compliance realistic? We'll look at the first 6 years of data between 2015 and 2021, the first phase of the system before the expansion was implemented. These are actual performance data of the pump and treat system. We're looking at PFAS and PFOA concentrations in the combined extraction water of the system before it goes through GAC to clean it prior to re-injection. PFAS is on the left and PFOA is on the right. The central line in each regression is the line of best fit. The upper and lower lines are the upper and lower confidence intervals set at 80%. This means the statistical probability of the regression being higher or lower than these bands is therefore 10% in either direction. Based on the extrapolation, when will the targets be met? Here we're looking at PFOA. The middle column reports the time to target of the extrapolated mean, the regression line of best fit. This gives us 37 years before the mean influent concentration is at compliance, taking us to the year 2052 based on the start date of 2015. The columns to the left and right are the statistical minimum and maximum based on the 80% confidence interval of the regression, 32 and 52 years respectively. By the same token, there is a 20% chance the mean lies outside this range, 10% probability the target is reached sooner, and 10% probability of it being reached later. But that was just PFOA. What about PFOS, the other specified compound? PFOS is declining more slowly, as we saw on the data graphs. It also has a higher starting concentration and a lower target. The remediation duration is therefore dictated by PFOS cleanup, and this will take some 5 times longer. Even if PFOA is cleaned up in the meantime, the system will still need to remain operational to address the PFOS. The probability of the mean concentration reaching the cleanup target within 100 years is less than 10%. But even then, these are the original targets from 2015. The revised targets of the 2017 health advisories are more stringent. The projected remedial duration is now between 150 and 433 years. And remember, these numbers are based on the extrapolated mean of the combined influent concentrations. We're looking at the concentration after the most contaminated water is blended with cleaner water from less impacted wells. The core concentrations in the migrating plume will therefore be higher. And in the end, it's these that will determine compliance. So what does this tell us? It tells us that the 30-year time to target estimate from 2014 is not realistic. Instead, centuries may be required to secure cleanup using the installed pump and treat system alone. We are, of course, extrapolating many multiples beyond the 7-year data set. This is too far to have any real predictive value in a numeric sense, but it is nevertheless plenty strong enough to support these simple conclusions. The relevance of this analysis is twofold. Firstly, where costs are accrued on an ongoing basis, it's necessary to know the duration of operation in order to perform a life cycle cost comparison. Secondly, it establishes that the two technologies are equivalent in their function. Both secure remediation through containment. But doesn't pump and treat remove contamination from the aquifer? Well, yes and no. Yes, some contamination is removed. No, all the contamination is not removed. We've seen this will be the case for at least the next 100 years. The aquifer is not freed of contamination and therefore remains contaminated even though some mass is removed and takes on a new waste life cycle. If the pump and treat system stops pumping, containment is lost and the plume begins to extend again. Both pump and treat and colloidal activated carbon therefore secure remediation through containment as defined by the US EPA for Superfund sites as relevant here. How did we determine the implementation cost of pump and treat and plume stop for comparison? For the pump and treat system, published costs are available with some digging. For the hypothetical plume stop barrier, we had to calculate the costs based on available published data obtained from multiple sources. To keep the comparison on a level field, the plume stop design matched the phases of the pump and treat design as if the two designs were conducted in parallel using the available data of that time. But the data requirements are different. Whereas an understanding of the groundwater capture zone is critical for hydraulic containment, the contaminant mass flux and its vertical and horizontal profile are critical for the design of a colloidal activated carbon barrier. The characterization reports that were available were based on pump and treat requirements. They're good reports for this purpose, but they did not contain all the data necessary for the colloidal carbon barrier designs, and this meant we had to undertake some creative data analysis to obtain the design information we needed. So how did we do it? The colloidal carbon design was based on mass flux. We can determine the mass flux to each well if we know the daily mass collected by each well and the capture plane. The catchment of each extraction well is available from ModPath modeling of particle tracks in published reports, summarized in this graphic. PFAS concentration data are also reported from each extraction well. The groundwater extraction rate is 2. We can take the horizontal dimensions of each well's catchment from the figures and the vertical plume dimensions from published profiling reports. This gives us the mass flux to each well because we now know the mass collected by each well and the surface area of the flux plane to that well, and so we can use the equation shown at the bottom of this slide. The mass flux can then be fed into the modeling software used for application designs with an individual model run for each of the 7 catchment zones. Summing these gives us a robust, flux-based, colloidal activated carbon demand calculation that we can use in the plume stop application design. The modeling software used in the present analysis is PlumeForce. The first version of PlumeForce was launched in 2016, and it has been steadily refined and expanded since. This is what I looked like when I started writing it, so be warned if you're thinking of entering this discipline. PlumeForce is an invaluable tool to support multiple stages of a reagent-based remediation project. We're using it here to support application design. The calculated PFOS and PFOA flux for each zone can be entered directly into the model. But although PFOS and PFOA are the only compliant species listed in the Wurtsmith Remediation Ordinance, they are not the only PFAS species present. There are many more PFAS species in the mix. All will compete for sorption sites on the activated carbon, and this competition must be computed in the model in order to determine how much carbon is needed. In this analysis, concentrations of other PFAS were based on their proportions relative to PFOS and PFOA as reported in the site investigation and monitoring reports. Further allowance was included for unreported PFAS species and also for competing co-contaminants and for natural organics. Separate model runs were undertaken for each extraction well catchment. PFOS and PFOA flux was up to 12 milligrams per meter squared per day and 3 milligrams per meter squared per day respectively. These are relatively high values for a PFAS site. Groundwater velocity was calculated from the pump and treat extraction rate that was balanced to secure the groundwater capture. The calculated velocity was 966 feet per year, presuming an effective porosity of 23%. Again, this is relatively fast. The exact value, though, is unimportant for the design, as in this case, the design is based on flux values which are not calculated from groundwater velocity. For each modelled zone, the colloidal carbon quantities were initially entered as the minimum dose required for reagent distribution through the specified target zones. For the least impacted zones towards the plume periphery, this already provided up to 47 years modelled longevity for PFOS and 55 years longevity for PFOA. For the most impacted zones towards the plume core, the colloidal carbon quantity was increased until the model longevity reached a minimum of 25 years for either species. This meant that each zone in the transect would require periodic carbon reapplications at a frequency ranging from 25 to 47 years, presuming the input concentration remained constant throughout this time. The colloidal carbon barrier costing was based on application by direct push injection into a target treatment zone extending between 15 and 30 feet below ground level, representing the upper 15 feet of the saturated zone where the PFAS plume was located. The costing further included an additional 20% commissioning allowance for each carbon application and periodic reapplication. This would typically comprise supplementary carbon applications at localized points based on groundwater analysis to ensure performance was tracking with the model design, and this might be conducted between 6 months and a year from the principal application in each case. To keep the cost assessments comparable, the carbon barrier alternative comprised 2 distinct stages to match those of the pump and treat installation. The location of the carbon barrier relative to the plume at the time of the initial pump and treat design is shown here in red. It extends 1,500 feet and is installed through 15 feet of aquifer to a maximum depth of 30 feet. The barrier thickness parallel to groundwater flow is 13 feet. There are 600 injection points in total, arranged in 2 rows. The resulting fraction of colloidal activated carbon painted onto the aquifer soil, the FCAC, is between 0.0022 and 0.0038. In quantity, this is about the same fraction we might expect from natural soil organic carbon, or FOC. It doesn't take up much pore volume and therefore does not materially impact groundwater flow. The difference is that it sorbs 1,000 times or so more PFAS, weight for weight, than the natural soil FOC. Here is the carbon extension barrier. Again, this is what our design would have been for this second phase if we were given the same objectives as the pump and treat extension at the same time. The downgradient plume concentrations are reducing owing to 4 years of upgradient pump and treat activity. But note that the plume figure minimum concentration shown here is still 100 times higher than the compliance concentrations. The barrier is shorter overall than the principal barrier upgradient, but is installed to a greater depth as the plume is diving a little. The projected longevity, and therefore the reapplication frequency, is 44 years, based again on the assumption that the source remains constant and ongoing throughout this time. This is clearly a conservative position, as there is already an observed decline. But the intention is for the cost comparison to tend towards conservatism rather than exaggeration of any difference. So how does the cost comparison shape up? Well, it's time to find out. This chart presents the comparative annual and cumulative costs of the two remediation approaches over the first 10 years of operation, 2015 to 2024 inclusive. The pump and treat spend is shown in red, and the carbon barrier spend is in green. We can see the principal capex of installation in 2015 for the initial system and in 2021 for the extension. Notably, the pump and treat capex is broadly equivalent for the first and second installation phases in 2015 and 2021, at a little below 4 million in each case. In contrast, the carbon barrier capex of the second phase is only about a third of that of the first phase. And this is because the lower contaminant flux reduces the carbon requirement and extends the barrier longevity, which in turn reduces the installation cost and the reapplication frequency. We can also see the impact of operational expenses, or OPEX, on the cost difference. The installation capex for the initial carbon barrier is actually higher than of the corresponding pump and treat installation. With the 20% commissioning contingency applied the following year, for a short period, the carbon barrier is the most expensive alternative. But pump and treat has operational expenses, whereas the carbon barrier has none. We can see these in red on the bar chart year by year. As the pump and treat OPEX costs accrue, the cumulative costs of the pump and treat option quickly overtake those of the carbon barrier option, as we can see in the diverging line plots. The impact of the OPEX difference on the overall cost comparison is shown clearly in the chart on the right. This shows the total cost of each alternative over the 2015 to 2024 period, broken down as CAPEX and OPEX. Groundwater monitoring costs are the same for each option and are therefore excluded from the comparison. But this is just the first 10 years. We determined earlier that the containment would need to be operational for at least 100 years as a standalone approach. So what about the costs moving forward? Well, numeric costs are one thing, but formal financial costs or investment projections accommodate value considerations, and the value of a dollar changes with time. Discounted present value, or DPV, discounts future costs based on estimates of interest. It is therefore an adjustment that accommodates the value of a delayed spend. Put in simple terms, money that is spent later could have been invested in the meantime, and the investment growth can be deducted from future costs. The cost of spending $100 next year is therefore less than $100 in this year's money. The DPV discount rate can also be combined with an inflation estimate. Published formal discount rates are available for federal projects, and these were used in the present analysis. This is the forward projection over a nominal 100-year period. The discount rate applied is 2.5%, accommodating inflation also. The future dollar costs increase due to inflation, but not as much as the delay in spend reduces them in present terms. The gradient of the curves therefore reduces over time as each year's spend becomes less in present terms. We can see the carbon barrier costs incrementally increasing as each of the zones along the barrier length are periodically repainted with carbon on their individual reapplication schedules after the initial 25-year minimum design longevity hiatus. But meanwhile, the pump and treat OPEX has continued to accrue year by year, leading to a significant difference in remedy cost. At the 30-year point, for example, the carbon barrier cumulative cost is 7.2 million compared to 19 million for pump and treat, making the carbon barrier 62% lower in cost. The principal saving is in the operational expense. Interestingly, the cost differential remains broadly the same proportion over time. These are the comparison intervals presented in the formal paper this webinar is drawn from. For those who prefer numbers over graphs, these are the numbers from the report used in the graph on the preceding slide. The colloidal activated carbon barrier is broadly a third of the cost of the pump and treat alternative over the greater part of the projected life cycle. I mentioned earlier that the cost comparison is deliberately conservative. If anything, the difference between the two approaches is underestimated rather than exaggerated. I'll take a moment to elaborate on this. Whenever assessment discretion is required, low positions have been taken for the pump and treat system and high positions have been taken for the carbon barrier. For example, pump and treat costs do not include provision for longer-term equipment replacement. If a pump and treat system had been installed in the 1920s, would we still be using the same pumps and hardware today, or would it have been replaced quite a few times by now? Replacement every 20 years or so, or even less, would not be unreasonable for many items. The carbon barrier costs assume no decline in input concentrations over time, although our earlier analysis of performance data did show a decline, especially for PFOA. Also, the pump and treat costs do not consider the implications on disposal costs of the 2024 designation of PFAS as hazardous substances under CERCLA, and this would be expected to increase the pump and treat costs. The real difference between the two approaches may therefore be greater than presented, and so critical scrutiny of the numbers would likely amplify the difference. So why did we not go with the best estimates rather than conservatism? The answer is that best estimates are arguable. There will always be a subjective dimension to them, and this makes them susceptible to bias, or indeed the suspicion of bias. In contrast, if conservative positions are taken, we have a least difference comparison. The true difference is likely to be greater, not smaller. The arguable component is therefore by how much the difference may be greater. For this paper, this means that the conclusions are robust and would not be changed by data uncertainties. All the same, this example is just one site. How representative is it? This is the Wurtsmith cost comparison graphic we looked at a few slides ago. And this is an analogous comparison at a UK airport undertaken by Mallet and others. Both compare the costs of a colloidal activated carbon barrier and a pump and treat system. In the case of Wurtsmith, the pump and treat system is installed, whereas the colloidal activated carbon barrier costs are calculated. For the UK airport, it's the other way around. The carbon barrier is installed and the pump and treat alternatives are calculated. The similarity is immediately evident on looking at the graphs, although the studies were entirely independent. For the UK airport, two different treatment options were considered for the pump and treat system: granular activated carbon, or GAC, the lower of the two projections, coloured orange on the graph, and foam fractionation, the higher of the two projections, coloured dark blue. The carbon barrier cost is 60 to 65% lower than the pump and treat costs. In the Wurtsmith comparison, the carbon barrier costs are 62% lower. Overall, therefore, the key takeaways from the Wurtsmith cost comparison are these. The colloidal activated carbon barrier presents a cost saving of over 60% compared to pump and treat. It is broadly a third of the cost at 30 years, and indeed throughout an extended life cycle projection. This comparison is deliberately conservative. The pump and treat cost projections may be low, and the carbon barrier cost projections may be high. Pump and treat extracts PFAS, but it will not clean up the aquifer within 100 years. The estimation on installation was for cleanup in 30 years, but performance projections suggest 200 years may still not be enough. This analysis is on a relatively high flux site, as indeed was the UK airport. The cost differential on high flux sites is generally smaller, so on other sites the cost differential is likely to be greater. We have seen, for example, that the carbon barrier installation capex was broadly the same as the pump and treat installation capex for the high flux first construction stage, but only about a third of the cost for the low flux extension stage. The greater longevity at the lower flux would reduce the periodic carbon reapplication costs and the reapplication frequency also. I'm going to briefly move beyond the Wurtsmith cost comparison paper and close with some other considerations beyond direct costs. The principal cost differences are down to the different operation and maintenance requirements as we've seen, and we can break this down a little. Groundwater monitoring costs are common to both approaches, but a carbon barrier does not have plant to monitor and maintain on a daily or weekly basis. It has no power requirements to operate, and it generates no waste. Power usage and waste generation invite environmental considerations beyond cost. Mallet et al. Performed a wider environmental comparison of pump and treat and colloidal activated carbon remediation of a PFAS plume at the UK airport site alongside the cost comparison we recently looked at. They calculated the raw material, energy and waste footprint of the carbon barrier was less than 5% of that of an equivalent pump and treat system based on installation and the first 15 years of operation. But the waste consideration goes beyond environmental footprint and immediate cost. Waste has a life cycle of its own. It also carries liabilities that have the potential to present further costs. In this paper, published about a year ago, the authors document unintentional PFAS releases reported for a wide range of waste handling, treatment and disposal activities. The arrows in the figure illustrate movements of PFAS during such activities. These include releases to air, soil, surface water and groundwater, each based on literature examples cited in the paper. The PFAS waste may pass through different treatment and disposal stages, and releases may potentially occur at any of these. PFAS have been detected in incinerator off-gases, for example, in incinerator ash, and even in landfill leachate from incinerator ash monofills. These have the potential to spread PFAS to other environmental compartments and to expose new receptors. They introduce the possibility of direct or joint and several liability for addressing the new release or the new release source. But surely pump and treat isn't new, and so this isn't anything new. Waste from treatment systems has been handled for years. Well, it is new for PFAS. In this regard, PFAS differ from more familiar groundwater contaminants in two important ways. They do not attenuate or biodegrade in the same way as conventional organic contaminants, and the concentrations that pose a problem are perhaps 1,000 times lower, and we're dealing here with concentrated wastes. Will this be a problem? Who can say? We're only just starting, and the track record is still to be written. But I believe it is important in a cost comparison to acknowledge areas where costs and liabilities may expand. The potential for release might be low, but with each year of operation, the possibility that a release will have occurred will grow. Over the century projection we considered when analysing cost, for example, even a once-in-100 years event becomes a certainty. And there is a difference between pump and treat and colloidal activated carbon barriers in this regard. Pump and treat, with whatever form of treatment, generates waste, as we've noted. In contrast, in situ colloidal activated carbon barriers do not. Let's briefly consider practicalities such as resilience, and we'll do this in our last few minutes in quick-fire FAQ mode. What happens if we stop repainting the carbon barrier? Answer: nothing for a long time. What happens if we stop pumping? containment is immediately lost. What happens in 25 to 40 years? We have to replace much of the pump and treat hardware, or we have to repaint the colloidal carbon barrier. And so, to close, pump and treat and colloidal activated carbon barriers are the principal remediation technologies for PFAS. Only these are classified as field implemented for groundwater by the ITRC. A robust cost comparison at the Wurtsmith Air Force Base shows colloidal activated carbon to be about a third of the cost of pump and treat. This analysis is conservative and it is consistent with other published comparisons. Pump and treat contains a plume but will not free an aquifer of contamination. Projected time to target of more than 100 years means considering pump and treat to be a cleanup technology is a fallacy. Pump and treat generates PFAS waste, but colloidal activated carbon barriers do not. Unintentional releases have the potential to expand liability and costs. The amount of information on in situ colloidal activated carbon treatment of PFAS, and indeed on colloidal activated carbon coupled with bioremediation for other contaminants, is rapidly increasing. Sticking with the US Department of Defense theme, CERDUP and ESTCP are the Department of Defense's installation innovation programs. In their own words, the programs prioritize common sense, cost-effective solutions that support operational effectiveness and reduce regulatory burdens at military installations. There are currently 10 formal colloidal carbon programs underway under CERDUP ESTCP, the first having started in 2020. The program has already generated a body of valuable publications, with more expected to follow as the initial projects reach their conclusion. And finally, a bibliography. These are the cost comparison publications cited in this webinar if you wish to take a quick screenshot. Most of the content of the webinar was drawn from the Wurtsmith publication on the left. The catalogue of documented unintentional PFAS releases from waste handling activities are described in this paper. And with that, I'll close. Thank you very much for attending this webinar and for listening.
All right, thank you, Jeremy. That concludes the formal section of our presentation. So at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a couple quick reminders. First, we will be sending out a brief survey after the webinar. We really appreciate your feedback, so please let us know how we did. Also, you will receive an email with the recording as soon as it is available. All right, so let's circle back to the questions here. Jeremy, first question is, why did you not include an estimate for the pump and treat hardware replacement, and what do you think it might be?
Okay, I didn't include it because it's arguable. The report takes a deliberate conservative position throughout, and so if the cost is arguable, let the argument be about how much higher the pump and treat cost will be, not whether it is higher or lower. But I think you also asked me what the cost might be, and we actually put this question to the engineering firm who installed the Wurtsmith pump and treat system. The answer we got was that after about 20 years, you pretty much expect to have to rip everything out and replace it. This would mean that the original capex cost, or at least a good deal of it, would come around again every 20 years as an additional $5 or $6 million or so.
Okay, all right, thanks, Jeremy. So here's another question. So you said that the Wurtsmith site and the other UK one you mentioned were high flux examples, and that for lower flux sites, the cost difference with pump and treat would be greater. Can you give it an idea about how much of a difference this would make? And then also related question to that, wouldn't the pump and treat cost be lower too if the flux was lower because it would have less PFAS to treat?
I think the answer to both of these is in the data that we've looked at. The second stage of the Wurtsmith installation had to address a far lower flux than the first stage. It was somewhere around 10% of the flux of the first stage, in fact. The pump and treat and the colloidal carbon barrier capex were about the same for the first stage, but at the lower flux of the second stage, the carbon barrier capex had reduced to about a third of the pump and treat capex for the same challenge. The projected colloidal carbon reapplication frequency was also lower at the lower flux, and this would have further increased the differences over time. Wouldn't the pump and treat costs be lower too at a lower flux, you might ask? Yes, they probably would, but not to the same degree. The waste treatment costs would be lower, but the pumping requirement for hydraulic containment and the related system maintenance would stay the same. And this is broadly what we saw at Wurtsmith.
Okay, so here's another question. Speaking of Wurtsmith, is why did you choose the Wurtsmith site for this comparison?
Well, that's an easy question. Because it has a long data history in the public domain, so it was ideal for data mining to do this analysis.
Okay, all right, so here's another question. It is your cost assessments and long-term projections assume the source would be ongoing. What would happen if the source was addressed?
That's a good question, and the answer is a little more complex. In the simplest terms, if the source is removed or even attenuated, the plume flux to be treated reduces, and this in turn reduces the cost of plume containment. The cost difference at the lower flux is bigger for colloidal carbon barriers than for pump and treat, as we just mentioned. But what if the source is removed entirely? Doesn't this make containment unnecessary? Well, this is where things get more complicated for PFAS. Without getting too granular here, an important characteristic of PFAS is that a lot more mass is contained in the plume footprint itself than would occur with more familiar contaminants. And this is because a larger proportion of the mass sorbs to the natural formation, especially the larger AFFF species like PFOS, PFOA, and PFHXS. And so this means that even if the source is addressed, mass in the plume footprint continues to bleed from this sorbed reservoir into the groundwater for an extended period. The result is that the plume dies far more slowly than we might expect after the head is cut off. It might be a long time before concentrations reduce, especially at a distance. Containment measures will therefore likely be needed throughout this time.
Okay, thanks, Jeremy. So here's another question. Isn't it better to remove PFAS rather than trap them in the ground?
If you could remove them, then perhaps yes. But we can't remove all the PFAS contamination and clean up an aquifer, as we've seen in this analysis. And so what do we gain by removing some of it? The aquifer stays contaminated. And importantly, what is the benefit of taking on the additional liabilities related to PFAS waste? Regenesis posted, in fact, an earlier webinar a couple of months ago that touched on this. We were fortunate to host Brian Gross of the law firm MG&M as the principal speaker. And the webinar, I think, is available on the Regenesis website. It aired about last March, I think. One of my take-homes from it was that following designation of PFOS and PFOA as hazardous substances under CERCLA, contributors to any site deemed contaminated with PFAS, perhaps a leaking landfill, could be hit with the costs of the investigation and cleanup. The liability faced would be strict, and it would also be joint and several, and contributors could be anyone in the chain, including originators and waste transporters. The investigation and cleanup costs would potentially be huge, so we could anticipate the EPA or other parties aggressively going after anyone they think can pay. And so, to answer your question, I would consider this an argument for keeping PFAS locked in the ground in situ. With the colloidal carbon barrier, we know where the PFAS is, we know it's not spreading, and we know it's not driving a risk. And so the PFAS and the liability remain contained.
All right, so thank you very much, Jeremy. That is going to be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. If you'd like to learn more about remediation technologies from Regenesis, please visit regenesis.com. Thanks again very much to our presenter, Dr. Jeremy Birnstingl, and thanks to everyone who could join us. Have a great day.